Good day, everyone, and welcome. I'm Jack Van Horn from the University of Virginia, and I am very proud to welcome you to this edition of our 2022-2023 Foundations of Biomedical Data Science Seminar Series. This lecture series is supported by UVA's Integrated Translational Health Institute of Virginia, the UVA Brain Institute, the College of Arts and Sciences, the School of Data Science, and through grants from the National Institutes of General Medical Sciences. Since 2016, the Foundations of Biomedical Data Science Seminar Series has focused on the use of data science methodologies, artificial intelligence, deep learning, and statistical modeling as they pertain to different themes in the biomedical and health sciences. This year's chosen theme is data science and the public health consequences of the COVID-19 pandemic, where each Friday we will enjoy presentations from leading thinkers about the issues, the promise, the opportunities, and the hurdles associated with understanding the secondary health effects of COVID-19. These include delayed health checkups and treatments, mental health, drug abuse, increased obesity, and the long lingering health effects associated with the SARS-CoV-19 virus. Participants selected for our Biomedical Data Science Innovation Lab program will leverage these presentations as vital material for our culminating in-person grant development workshop to be held at the Lodge at St. Edward's Park in Seattle, Washington in June of 2023. Today, I am delighted to welcome our speaker, Dr. Christopher Murray, who is the Chair of Health Metric Sciences at the University of Washington and the Director of the Institute for Health Metrics and Evaluation. He holds his MD from Harvard. He has a DPhil from Oxford, and he did his undergraduate work also at Harvard. His career has focused on improving population health worldwide through better evidence. He is a physician and health economist, and work has led to the development of innovative methods to strengthen health measurement, analyze the performance of health systems, understand the drivers of health, and to produce forecasts of the future states of health. In continuing with our 2022-2023 Biomedical Data Science Seminar Series, Chris's talk today is entitled, "How Well Did the World Do Modeling COVID?" Dr. Murray will describe how he and his team searched the body of COVID-19 modeling globally from the start of the pandemic and reviewed over 7,000 different models and articles and websites. Of these, a number of them had available data, and then they were able to evaluate the performance of these models against what happened during the pandemic using performance measures that included forecasting skill. They were able to draw a number of different conclusions, which Chris is going to summarize for us. And he's going to make some recommendations on how we can do a better job in the future and share some lessons learned about how to validate models and global health more broadly. As always, we are streaming this lecture live and for recording via YouTube. And if you are watching on YouTube, thank you so much for joining us. Also, our specially selected 2022-2023 Biomedical Data Science Innovation Lab participants and alumni are encouraged to submit any questions they have via the chat feature in their Zoom sessions. I will synthesize these questions and ask them on your behalf during the last 10 minutes or so of the lecture. And with that, welcome, Dr. Murray. We are super excited to hear from you today.
Thank you very much. Happy to be here. So I'm going to talk about our effort to look at the sort of infectious disease modeling community response to COVID. We were part of that community that responded and participated as one of the modeling groups, the many modeling groups out there, and modeled COVID really from March 2020 on our part right through till January of this year. So this is a perspective both of looking at all the published and other models out there, and also one from having tried to do this. So as you may or may not know, there was quite a response from the modeling community to the pandemic in this country and in many other countries. I won't go into the sort of systematic review part of this, of trying to find every published study, try to contact all the groups that contributed to the CDC-led Modeling Ensemble Hub and the European Hub and all the other efforts. We also tried to reach out to different governments and ask them which models they used, and in some cases obtained modeling efforts that weren't published or in the public domain. We have found meeting our inclusion criteria for models, which was at least 5 efforts. So there's a number of one-offs that we found and didn't really spend time evaluating, but groups that made at least five releases of their model we included, and we end up with more than 300 that meet that criteria. Now, I'm going to take a large diversion into how we should or should not evaluate performance of modeling, because I think if I don't do that, then the conclusions on COVID are somewhat shaky. And interestingly, the infectious disease modeling community historically has not paid much attention to their performance in forecasting, as opposed to other disciplines that I'm going to draw on, like weather, climate, and economics. So the diversion will begin with trying to go back on the history of thinking about forecasting, both philosophically and quantitatively, look at the sort of major themes of forecasts evaluation, look at another case, namely the IMF's effort to predict income, and then dive into the results of looking at all the COVID models, and then round out with general observations about how we might do a better job. As a spoiler alert, I think the key theme of this is the infectious disease modeling community did a very bad job. But let me try to carry you along with that. So first, forecasting has been around a long time. There's books on forecasting. There's a nice book on the history of economic forecasting going back to even the 1890s. But there was really quite a lot of technical discussion about how does one evaluate forecasting in the 1930s. Even Keynes commented on this, and there's a paper by Tinbergen in 1939 on more quantitative thinking about evaluating forecasts. So this is not new terrain. We have intellectually an 80-year history of forecast evaluation. It's that history just has not made it into there's some exceptions, into the infectious disease modeling world. Perhaps the most sophisticated in terms of the use of routine evaluation of forecasts is the weather community. And I will come back to that over and over, just how we can learn a lot from the way the scientific community around weather forecasting and even the World Meteorological Organization's efforts to encourage standardized metrics for evaluation of forecasts. Now, I'm going to emphasize weather and economic forecasting, but many fields, sports forecasting, agriculture, others, use forecasts and evaluate those forecasts. And with a few exceptions, there's a flu group that has done some forecast evaluation in the past, and then a COVID modeling ensemble that used one particular approach to forecast evaluation. There's very little of this in the infectious disease world. Now, I'm going to end up showing you skill metrics because the forecast community in weather, climate, economics, and others have tended towards, since the 1980s, measures that are called skill, which is for a given error metric, how you evaluate, how good your forecast is, comparing it to a very simple baseline model, then can give you a 0-1 scaled metric, which is very attractive because then you don't get caught up in what does it mean, a 0.032 of a root mean squared error for one thing and a 6 in another space. They're not comparable numbers, whereas skill is really quite comparable because it's formulated as 1 minus the error of your favorite error metric for your model, divided by the error of a particular baseline model. For weather, that's super easy because the baseline model is the historic average of the weather tomorrow from climatological data. For economic forecasting, it's historic growth rates. And so you can go along those lines. And when we come to COVID, it'll be an interesting question of what is the simple baseline model. Skills not only useful as a way of thinking about measuring forecast performance, but it is also handy to address the question of the skill horizon. When does skill go to 0 compared to a very simple baseline model? In weather, that's at about 2 weeks. It's been getting longer and longer as modeling has gotten better. And in economic forecasting, it's a number of years into the future. And the big question that's still outstanding on COVID is, what is the skill horizon for infectious disease or for COVID modeling? Now, there is a philosophical issue that comes up a lot. It came up in the literature around economic forecasting right back in the 30s and 40s. And you hear it a lot around COVID. And that is, if my audience is the government and I model out what I think is going to happen in the future, and then the government uses my model because I provide both a forecast and some alternative scenarios, and I persuade the government to change policy, let's say adopt mask use, have a mask mandate, then I shouldn't be held accountable for the successful use of my model to change policy. And it's very interesting. I think the most sophisticated treatment of this philosophical issue is from the Organization of Economic Cooperation and Development, OECD, which is basically the high income economies that belong to the OECD. And they do a lot of income forecasting. And I think way back 40 years ago, they framed that if you are only modeling for government and it's not publicly available and nobody is taking an action based on that, then that argument might hold true, that maybe you should have a conditional assessment of what happened, conditional on, in your model, of what was the policy regime the government adopted. But their argument was that, in fact, almost always, think the Federal Reserve on inflation or the Federal Reserve on GDP growth or the IMF on GDP growth, these forecasts are not just for government. They get into the public space, and many private actors, companies, individuals take action based on them. And therefore, while in theory your forecast may change policy, you as a forecaster should be accountable, if the public knows about the forecast, for also predicting how individuals and governments will act. And so that should be part and parcel of the forecasting business. And therefore, we should be able to and want to report on forecast skill and any metric you would like. We'll probably come back in Q&A to this sort of philosophical question. Now, the economists are very focused, as are some other fields, geophysics, for example, on measures of accuracy. How well does your forecast, the mean estimate of your forecast or the point estimate, compare to what actually happened? And many economic forecasts to this day do not provide uncertainty. They just say, we think the most likely growth rate for the US economy in the next quarter is 1.2%. There is some growth of probabilistic forecasting, but not a lot. It's still dominated by point estimates because that's actually what most decision makers act on. And again, a big philosophical debate about how important is uncertainty, and we'll come back to that. Here's a review of economic forecasting that was published in 2022 by Buderak, of just going through in a systematic review of all the different error metrics used in the economic forecasting world, and divided sort of into two large buckets: metrics that are in the units of whatever you care about, and this is usually growth rates, the absolute error of various types in growth rates, and then metrics that refer to some version of relative error, whether it's percents or ratios or even somewhat more complex measures as shown here. So same issue will come up with COVID. Now, another area, just to get to how messy this whole metric space is here's a paper in 2021 of a huge range of metrics in Limon's paper used in geophysics model performance assessment. And so, as you know, there's a wide array. many of them overlapping with what's in the economics literature. Now, there's a way to capture many, but not all of those measures in a general family of error metrics, where you take the absolute value shown here as, absolute value of y minus y hat in the numerator and raise that to a power alpha. That then encompasses people who are interested in mean absolute error or mean squared error, alpha being 1 or 2. And then in the denominator, you can capture this issue of absolute error versus relative error by dividing by y. To avoid the situation where you divide by 0, you put a little number called epsilon in there just to avoid the possibility of dividing by 0. And then you raise that absolute value to beta, where beta is 1. These are measures of relative error. Beta is 0. These are measures of absolute error and anything in between. Now, the last little bit of this is theta, which is the notion to make the results robust to outliers, because these error measures, particularly when alpha gets greater than 1, doing a bad forecast in 1 week for one location can make your overall error look terrible. And I will show this for COVID. And so the theta term here is to, quote, Windsorize the error function so that if your error is above some value, theta, you don't keep making that contribution to the overall error measure larger and larger. Now, it's easier to see this in a visual. So if you think about an error metric, this is true for, in a likelihood function, but just in terms of these performance metrics, you can think of it, visualize these different approaches by showing the absolute value of the error on the x-axis and the loss that you're going to calculate on the y-axis. And, mean squared error is the green line. Error of 2 gets a loss of 4, the square, and a linear one is the light green line, where an error of 2 gets a weight of 2 in the loss function. So you can see that in the difference between the squared error and the linear, of course, is that you are really saying, I don't want to make large errors. In the case of COVID, that large errors are much worse than a series of smaller errors. Now, the Windsorizing says, in this case, at the value of 2, you are going to hold the loss at a flat line. And so you get the gray line for a Windsorized loss function. And a common measure, the one that we use a lot, and I will show you, is Windsorized root mean squared error, where you Windsorize the error at some percentile of the observed absolute error. We often use 95%. So once you're above the 95th percentile of error, you get the same, bad weight. It's not getting worse and worse and worse. And I'll show you why this turns out to be important. Now, there's a group out there that I don't think is relevant to COVID that actually want to have a concave loss function shown where an alpha is less than 1. And there are certain applications out there where that might be interesting, but it is an unusual shape. Now, in weather, in contrast to economic forecasting, forecasts are mostly probabilistic. And so there's a different set of metrics that have emerged for predicting, what's the probability of rain tomorrow. And these go back to the 1950s. There's, again, a huge array of these measures. The main ones are listed here: reliability measures, coverage versus accuracy plot, where you count how in your 95% uncertainty interval, what percent of the time the truth or the future shows up in that interval. And I'll give a little bit more detail about Breyer scores, ranked probability scores, and then continuous ranked probability scores. So using some concrete results, here is the UK Met Office plot of reliability. And this is for their midterm 6-month out forecasts, or actually, no, 2 to 4 month out forecasts of whether the temperature will be higher than, equal to, or less than climatological averages. So it's for weather. This is long range. rough forecasting. And on the x-axis, they show the probability of being in those three buckets. And on the y-axis, they show the observed probability. So if you take all the forecasts of 50%, what was the frequency in reality of being above, in the case of the red line, of being above normal temperature? And you want your model to be on the 45-degree line, right? And the fact that these weather forecasts, when the probability is low, the truth is higher, and when the probability is high, the truth is lower, points to the lack of reliability of the forecast, which is worse for being in the middle and slightly better for predicting too hot or too low, too cold. Another way of using the same forecasts, again, using the UK Met Office example, is to use an ROC curve. These are receiver operating curves. I'm sure most of you are familiar with these for predicting a dichotomous outcome. You have the false positive rate and the true positive rate, false positive on X, true on Y, and you want to be up on the top left corner. And then the ROC, you can integrate the area between the curve and a 45-degree line to get a summary measure of that. And again, you can see this difference in performance for predicting high and low versus predicting in the middle. Interestingly, the weather community is sophisticated enough that they compute these metrics, whatever they're looking at, whether it's weather or mid-range or climate, by location, and they produce maps showing you where models did worse or better. So the dark reds are where they're doing well, and the blues are where they're doing poorly, and out over the oceans, they seem to do rather well, whereas they do not as well in a number of the land masses. Other probability measures. Breyer in 1950 came up with a very simple idea of taking the predicted probability of an outcome minus the observed, which is either 0 or 1 of an outcome, let's say rain more than 2 millimeters, and then just squaring that and then adding that up across all your predictions, dividing it, and you get the Breyer score, which is actually still widely used. There's a version of the Breyer score where you have a polytomous prediction. Think of in COVID, the analog would be predicting COVID incidence is low, medium, high, very high. You can calculate your Breyer score for each of those categories and then sum up over categories and over time, and you get a ranked probability score. And then the final version of this is the continuous ranked probability score, where you have a continuous curve of prediction, the red line, and then the actual observed probability of the event is the blue line, and you compute the red area between your cumulative probability distribution of the prediction for Y compared to what was observed for Y. Now, there's a key distinction here, which is sensitivity to outliers, which in the case of COVID is going to turn out to be super important. If you use a continuous probability rank score, you are very sensitive to crazy outliers. Let's say you made a really bad job one week and your model went crazy and you predicted a massive epidemic and it didn't occur in one place. That can swamp your overall CRPS. Whereas in the ranked probability score here, if you set the threshold at some level, you say, I'm interested if I predicted very high, but I'm going to give the same weight to the loss of predicting very high and absolutely insane. The RPS, as the same thing as Windsorizing on the accuracy measures, then builds in some resistance to the extreme outliers. Now, just to remind everybody that the weather community routinely, like every week, for most models, is reporting their skill. And they're not only reporting skill, but they're comparing their skill to the main competitors they have. And in the weather world, because weather models are really quite complex, there's not that many models that are modeling for the world. And most of them are listed here, and you get pretty routine assessments of skill. Okay, so that's some background history on skill and the metrics. And now we're going to turn to two cases, one very quickly on income, because I think income is important. It's a super complicated task because human behavior and the policy response matters a lot for predicting income. And then we'll turn to COVID. And the reason I want to show income is that I too often hear from the infectious disease modeling community, oh, it's too hard. That's why we do so badly. But in fact, if you think about the complexity of economies, they are super complex entities and with an enormous amount of individual behavior response as well as policy response. So I'm now comparing two measures of skill for IMF forecasts over the last 25 years. So twice a year, the International Monetary Fund predicts the next 5 years economic growth for every country in the world. And so there's a nice time series of their forecasts. They're all publicly available. You can go play with them yourself. And they have they predict many indicators, but the one I'm focusing on here is GDP growth rates. And they predict them both in what are called constant dollars on the left, which is after correcting for inflation. And they predict nominal dollars, actual dollars that you go and spend, which are called current prices, which include economic growth and inflation. And what we're seeing here is a comparison of just two skill measures. The skill measure on the x-axis is Windsorized root mean squared error, and on the y-axis is without the Windsoring. So just to show that skill, once you Windsorize for a number of the predictions, is better because you are not taking the 2 or 3 countries they do a terrible job on and really having that drive the overall assessment. To give you some examples, in other modeling that we do, completely unrelated to COVID, we get not uncommonly an example of where one modeling strategy in 99% of the cases gives you smaller, better accuracy, but in 1% of the cases worse. And that 1% is large enough that the summary measure of root mean squared error is worse, even though the model is better 99% of the time. Whereas in the Windsorized measure, you take away that, and it sort of accords more to your intuition that if you're doing better in 99% of the cases, your summary measure will look better. Here's another comparison, again, for skill. Skill on the x-axis here is just what we were showing, Windsorized root mean squared error. And on the y-axis is now a relative measure. And it's just to point out that there's very little relationship between skill predicting the absolute GDP growth rate versus the percent error or the relative error in the growth rate. And that's often because when you have a small growth rate, like 0.1%, and you predict 0.3%, well, that's a 200% error, and that looks really bad at those measures. So some people have uses for relative measures, but they're very unusual and have unusual properties. So last slide before we move to COVID, which is how good is the IMF at predicting? Well, for constant prices, and here I'm comparing two baseline models. A baseline model that just says GDP growth rate will be 0 into the future, which is a sort of not a great model. And then the 4-year historical average growth rate is what you predict into the future. And for current prices on the right-hand side, that model, the baseline model of the 4-year growth rate, then IMF forecasts have, skill of 0.4 in the first 3 months, dropping down to a skill that's around 0.15 on a 0-1 scale, and then interestingly sort of increasing over time, going up to a skill of about 0.25 by 5 years, 60 months. If you have a really bad baseline model, namely that the economies on average will not grow at all, which historically is not the case, shown in blue, then you make the skill of their models look better. And this is a little bit of a game that exists in the forecast skill world, which is if you pick a really bad baseline model, you can make your skill look better. So just a warning there. On the left-hand side, skill is much worse once you get past, 1 year, down below 0.1. And that's because it's in constant prices. So now on the left, you have to predict both inflation and GDP growth. So the difference between the two means that the IMF has been historically better, higher skill at predicting what's going to happen in nominal dollars, less good at dividing that future growth into what's inflation versus not. Okay, let's go to COVID. Let's start with reliability. And I'm going to show these plots in some cases for US models and for all other locations combined. For reliability, I'm just going to, I'll do the same thing here. So for reliability, these are all models, about 80 of them combined. And what is their reliability? So you take all the predictions of being above a certain threshold. This is for predictions of the death rate from COVID. And you can see if the threshold is how well do I predict the death rate being over, let's say, three per 100,000, which, by the way, is not a particularly low death rate, but still, then you can see there's almost no information content in the forecasts in aggregate because it's a flat line and it should be on the 45-degree line. So I predict 50% being above 3, and what I observe is during the pandemic was for those forecasts that 95% you're above 3. So lots and lots of forecasts that were too low. As well, if you look at the orange line of 180 per 100,000, when I predict, when the modeling community on average predicts 80% chance of being at a high level, huge level, 180 per 100,000, the observed probability is about 60%. So over predicting really high surges. And this has been a characteristic of some of the models throughout the pandemic. Here's the same graph for non-US locations. And it looks a little better, actually. But in general, the slope, instead of being 45 degrees, is actually quite flat. And the flatter these lines are, the less information content there is in the prediction. So if you were to compare this to the reliability plot we saw for 3 to 6 month forecasts of temperature, certainly not doing as well as those. Now we're going to go on to skill of various types, and the question, of course, is the baseline model. You saw how the choice of the baseline makes a difference for income forecasting. And so for COVID, what we picked as a baseline, and I think others have as well, in like the CDC ensemble efforts at looking at skill, is COVID staying constant. From the last measurement, just hold it constant. So it's a super simplistic model. So you would have hoped that we would, the modeling community would easily beat that. Now, skill, the relationship of skill will matter if you do or do not take into account the outliers. And this is one way to visualize that. I'm showing Windsorized skill, at Windsorizing at the 95th percentile of the difference between Y and Y hat, in this case, the COVID death rate, versus just the root mean squared error of the death rate. And obviously the root mean squared error is worse, and skill is worse when you use that because you were affected by outliers. But it has a pretty large effect in the case of skill. And here's another comparison. This is CRPS skill, which is outlier sensitive. and then Windsorized Skill looking only at accuracy. Remember, CRPS is sort of a joint measure of uncertainty and accuracy. And important to note that skill in those two different metrics is really quite different. So you have positive skill for CRPS that can have negative Windsorized skill. So just to note that, and vice versa. Okay. So let's start with basic. Here's graphs for modeling efforts throughout the pandemic. So just everything that's been done. We're talking actually millions of forecasts across the different groups by week and week out. Lump them all together, put forecast week into the future on the x-axis, and inside and outside the US, and basically on average, the modeling community has had negative skill. So we're not talking about, was skill 0.2, 0.4, 0.6, 0.8. We're saying that we were worse than a flatline forecast. So this is what I would describe as a massive fail for the infectious disease modeling community. However, if you go to Windsorized Skill, where you say, okay, we're not going to have the overall judgment be driven by the crazy forecast you made for one state in the US or one country in Africa or wherever, that something just went wildly wrong. You released a forecast that was, impossible, and that throws off those metrics. Because, by the way, lots of modeling groups did do that. They just didn't have the quality control to even stop on releasing things where something had clearly gone wildly wrong. So if you give people the benefit of the doubt on that sense and Windsorized Skill, then you get a less depressing picture, but still pretty poor. Namely, unlike weather and economic forecasting, where you get the classic curve where skill is greatest 1 week out or 1 unit of time out, 1 year, 1 day, 1 week, and then declines towards zero, and you get to the skill horizon. We see the opposite relationship in the US, where skill was worse than a flatline forecast out to about 3 weeks, then actually becomes positive and goes up and stays positive. And you see this bump at 15 weeks. And this is compositional bias, that namely the modeling groups that did longer range forecasts on average had better skill. So as you go more and more weeks out on this graph, you're getting to that subset of modeling groups that actually fared better. And that's why skill bumps up at 15 weeks. And same story for outside the US, you had negative skill out to 14 weeks, and then you get, a little bit of skill at the tail end. Now, what about the relationship between coverage, doing a good job on uncertainty for COVID, and accuracy, doing a good job on the point estimate? And this shows you for each modeling group across whatever they modeled throughout the pandemic, Windsorized Skill on the x-axis and coverage of the uncertainty intervals on y. You want the coverage of your 95% uncertainty interval to be 0.95. So you want to be at 0.95 on the y-axis, and you want to be as far out on the right-hand side as you can be for skill. And several observations here. First, there's no relationship between coverage and accuracy. So it's not the case in general that those that had more accurate models had better uncertainty intervals. They're just sort of unrelated dimensions here. Secondly, there's a cluster of models up in the top right that had, for short range forecasts, 1, 2, 3 weeks, good coverage and skill of about 0.25. And those, it turns out, tend to be models that are, in those cases, for one location. So there's a little cluster of modeling groups that did forecasts for one location, and they did a good job in both dimensions. And then there's there's these, as you can tell by the colors, some of the groups that do long-range forecasting, including ourselves down here on the bottom right, with moderate skill, but uncertainty intervals were too small. And we'll come back to calibration at the end of this presentation. What about the question of, did we learn as a community to do a better job during the pandemic? So here's skill during the course of the pandemic. So now the x-axis is calendar week. And there's no indication here that as a community, the infectious disease modeling community, including extreme errors, did a better job over time. So what about for Windsorized Skill? And in the US, you can see that there were periods where skill went up. For example, in the period in the sort of April, May, June of 2021, before Delta hit most places. And then when Delta hit, still dropped way down because people didn't anticipate it. The red line dips. Similar story as we get into 2022, where there was a drop in skill as Omicron came on board. Models adjusted, skill went back up, and then BA.5 came along and subsequent waves of Omicron, and skill got dramatically worse. So overall, both in the US and out, no clear signal that the community learned to do a better job. Here's a dynamic map of skill by location. And what's interesting here is that regardless of the week out, modeling, all models participating, and I'll let it play again, did a really poor job for sub-Saharan Africa, and a very poor job in East and Southeast Asia, with the exception of Malaysia. And then you get this phenomenon that skill goes up towards the end. And again, that's compositional bias, where the small set of groups that do the longer range forecasting on average had higher skill. Okay, so rather depressing if you're in infectious disease modeling, as we are. So what conclusions can we draw from all this? So first off, many modeling groups struggled with the fundamental data they were fitting their models to. They did not have the resources, or perhaps time or inclination or skill set, to do the deep dive into the data to make sense of it. And they ended up reflecting in their models really crazy data errors that were in the real time of the pandemic being released and not being caught and being dealt with. And that's true both for the outcomes, incidents, reported cases, hospitalizations, deaths, but also for all the variables that might go into a model, such as social distancing or mask use and the other. The other thing that many groups did on the data front was, because they didn't have the time or the energy to go into the details of the data, they made extreme assumptions that the infection detection rate remained constant. For example, the Department of Defense had a whole modeling effort throughout the first year of the pandemic, where they assumed that the infection detection rate was 100%. And of course, they knew it was not, but they just didn't have the strategy to deal with that. So at our end, we developed an attempt to triangulate using cases, hospital admissions, deaths, and the seroprevalence data shown on the right in the purple dots, corrected for various biases in it, to try to, in real time, compute each week what some of these key parameters were, like the infection detection rate, the infection hospitalization rate, and the infection fatality rate, and how they were changing. And that turned out to be super important, at least from our view, of sort of that data triangulation effort. And yet we had huge divergence across modeling groups on some of the basics, like the IFR, the IHR, or the IDR. Another basic insight is that many modeling groups stood up, stepped up to the challenge. They said, I'm an infectious disease modeler, or I'm a modeler in general, I'm a data scientist. This is a national global crisis. I'm going to throw my hat in the ring and participate, which was great to see people step up and try to help. But many of those models were simple SEIR models in the classic susceptible, exposed, infected, recovered, ordinary differential equation box models. And they used simple fixed parameters like R naught, and then never changed their model, despite all the learning during the pandemic and the role of variants, the role of vaccination, the role of antivirals, the role of seasonality, the role of human behavior, the role of mask use, and the like. And so, incredible, focus on a simplistic model and not changing. Most models, the vast majority, over 95%, made no attempt to build into their models human behavioral response, a social distancing and mask use, for example, when things got bad, nor did they explicitly try to model how governments would respond when things got out of control. And I can give you many anecdotes, having talked to many sort of political leaders during the pandemic, of modeling groups advising them with these very strange, assumptions that were leading to extreme conclusions and extreme requests for resources earlier in the pandemic. And when you asked modeling groups why, their response was, we don't know how, or it's out of scope, or we just don't really know how to deal with behavior and policy. Perhaps the most damning, I think, is the culture of not reporting skill. However you want to measure Windsorized skill, whatever your favorite measure of skill, there is no culture in the infectious disease modeling world of doing this. There's some bright exceptions. The CDC modeling ensemble, which was only for short-run forecasts, 4 weeks, but nevertheless, they did periodically try to look at skill. So that's a bright spot in this story. But in general, the infectious disease modeling community resists the routine reporting of skill. And in my view, we will never see better performance from infectious disease modeling for forecasting purposes unless we adopt what other fields do, which is a culture of routine, real-time reporting around skill. Bizarrely, as a reflection of not looking at skill, modeling efforts that had negative skill throughout the pandemic kept going. So you had groups that were notably worse than a flatline forecast that just kept making forecasts. And, that doesn't happen in other fields. If you think about sports forecasting and what bookies do, odds makers do, they will lose money if they did that. And so there's a self-correcting mechanism in that community. And in income forecasting and weather forecasting, there is a culture of routine reporting. So really bad modeling efforts do tend to drop out pretty quickly. Now, little side note, we shouldn't be too harsh on the folks that stepped up and tried and did a bad job. At least they tried. But there's a whole group of modeling and some very, very accomplished, well-known infectious disease modeling groups that never made forecasts. They were pundits on the sideline and they would criticize forecasts, but never made their own. And I think it's a pretty simple diagnostic there. They never made forecasts because they were worried about having poor skill and didn't want to expose themselves to that sort of critique publicly. But it is curious that, if not for COVID, when would you ever step up and do forecasting? Another thing that I think we have not learned from the weather community is that there's a very simple post hoc fix used in the weather community to fix poor coverage of model predictions or to fix reliability, which is they routinely look at their model performance in the last period of time and say, if I predicted rain 60% of the time and I only observe rain 50% of the time, then I post hoc take my model prediction of 60% and call it 50%. And that post hoc calibration improves performance. And it's a pretty simple device that we could import into infectious disease modeling or COVID modeling or whatever else comes down the pike, so that we both get the uncertainty intervals to be accurate and also could shift the mean of those predictions or the point estimate to get on the 45-degree line. You pay a price for calibration, which is you become less capable, but true, of predicting either end, 0 probability or 100% probability. But for COVID modeling, that's almost never the case, right? Nobody's ever been that great. We haven't seen skill up above, on average, about a 0.25 or a 0.3. So my last slide here, and then we'll have some Q&A, is what do we do in the future? And we get asked this question a lot. And I think my view of the strategy is sort of threefold. One, as in the weather world, we're probably all better off if there are 10 modeling groups that are that have demonstrably good, positive skill, that you try to build them up and have them commit to routine and real-time reporting of skills, so they compete during the process of an epidemic to get better and learn from each other. And you never will, as we saw during COVID, if you don't do that. But the idea that we'll have hundreds of modeling groups with good skills seems hard to do, given all the work that needs to go into keeping up with a disease as it evolves. Secondly, a lot of the problems in models do trace back to lack of data or the cost of acquiring some of the critical data points. And part of that is governments themselves, US being an example, were reluctant or very slow to release data. And there's many reasons behind that. Some of the analysts within CDC wanting to publish papers before the other people see the data. Some worried about the public misinterpretation of the data. Long list. But bottom line is we're all safer and better off if there is a commitment to release the relevant data in a very short time period. And lastly, I think, and this is a little bit more questionable because I don't have proof of it, but part of the problem of why modeling groups did not adapt to the virus as it changed, add in vaccination, add in antivirals, add in waning immunity, which is quite complex, is that those make models much more complex and harder to converge and require a certain, both access to computation and a certain set of skills. And it might be the case for those sort of models and for machine learning models that having some standardized tools that have those capabilities built in that are widely shared, open source, and could then be changed and adapted by different groups, because you don't want everybody to have the same model. I think, that's certainly not what other communities do to do a better job. They have large ensembles of quite different models, but you still need to help groups get over the hurdle of the challenge of incorporating some of these more complex phenomena like waning immunity. So those are some reflections on how we might do better next time round, given what I'll have to confess is a rather depressing story of how the modeling community stepped up for the COVID-19 pandemic.
Chris, thank you so much. I'm filled with questions. One of the things you showed a slide early in your talk, which was all the different types of kind of cost functions that people evaluated their metrics with respect to, usually some sort of ratio of signal to noise, in however you want to define that. What question is that people, I presume, make a choice of what they want the denominator of their baseline model error to be, or rather it's basically derived from their model. Does that seem a little bit, it seems like it would be difficult to compare across models because they don't share a common denominator. And so that skill metric is sort of skill with respect to that particular model, but it still, doesn't have a common denominator. Is that perception correct?
No, I don't think so. I think the baseline model, which is, what you have to have the error for your baseline model to calculate skill. If, for example, all the COVID comparisons, it's the exact same baseline. It's that COVID stays flat.
Okay.
So as long as the baseline is the same thing, then for a given skill metric, RMSE, mean squared error, whatever you want, CRPS, then that's the beauty of skill. It is comparable.
Okay.
Is a skill comparing weather skill 0-1 of weather compared to climatological average comparable to a COVID model compared to a flatline model? Yes and no. I think as long as you pick the baseline to be the best simple baseline for that field, I think in some sense you're still comparable. How much better are you than a very naive model? In the case of COVID, you might come along in the future as say, flatline is a little extreme. It's too simple. And so, in fact, we're skewing towards making the models look good by picking a very simplistic baseline.
Mm-hmm.
But already we look so bad that I'm not sure that gets us off the hook.
Are there any attempts to look at more information theoretical metrics such as KL divergence or other things that try to work directly on the probabilities from an information theoretical point of view?
There are, there's an information theory justification, if you will, for the CRPS, the continuous rank probability score. There are some other measures like Thiel's measure that are grounded in information theory. So there are a number of error metrics where people have tried to link to information theory in some way.
Are there any evolutionary approaches to this where you sort of mentioned skill, which is, I suppose, one metric of overall performance, but if even skill isn't working out very well, is there something like model fitness that would allow you to say, okay, in this generation of the model run or whatever it is, that it did a good job, therefore it lives on. Those that don't do well then fall out and they basically go extinct. Is there any sort of movement towards that would help?
No, and in fact, that's it's another way of framing what I'm calling for, which is you would hope if there was, as in weather, routine prediction reporting of skill, that bad models would drop out, right? And we did not see that at all.
Yeah, I mean, you commented on that. Models that were doing poorly just kept reporting poor numbers, and they did not just go by the wayside. From an evolutionary point of view, that the ones with the best fitness should have continued to the next generation, and those that didn't die off were still kind of around.
No, we saw no shift, and I guess that graph of skill over calendar week is the most depressing in a sense. That as an academic community, not to point fingers at any one group, but as a group, as the totality of the infectious modeling community, no self-realization, no evolution towards better models.
As we have a group of newly minted faculty members, many times building their research networks and starting their careers working in this space, what sort of advice do you have as they get started?
I think it applies, this notion of skill applies not just to forecasting, but just to prediction in general. Some people call it forecasting or nowcasting, whatever you want to call it. And I just think it's very painful, right, for the modeling groups to look at their performance, because it's very easy to, if you don't look at the metrics, especially skill metrics, it's very easy to delude yourself for some reason that things are going well. And so I think it's the discipline of looking at some measure of skill and saying, wait, because everyone not everyone, people in our field love complexity, right? Love to come up with, whether machine learning or Bayesian statistical models, revel in complexity. And it's a good discipline to say, hold on a second, does the more complicated approach actually give me better forecasts? And when you have numbers that are where the scale is sort of incomparable and meaningless, it's very easy to miss the fact that you may not have skill over something like a flatline model, which is a pretty low bar to get to. So just that intellectual honesty with yourself is a good discipline to adopt.
Do you think that there's a case for parsimony here? You mentioned like the level of complexity. People always like to go for the more what is maybe trendy or apparently more sophisticated, but maybe sometimes simple is better.
Sometimes, and I think that's a very tricky road to walk, because sometimes simplicity is not better because some phenomena are truly complex, but sometimes simplicity is better. And I tell my junior faculty here that are working on these sort of issues, they do tend to fall into lumpers and splitters, right? There's a group of people who just see any result or problem and think of the ways in which more complexity will enhance the assessment. And then we have the reverse phenomenon, people who really like to go for simplicity. And it's sort of getting that balance right. And I think the only way we can do that is with, guided by some sort of metrics.
Well, Chris, thank you so much for sharing this work with us, and lots of food for thought about how we kind of evaluate these models, their ability to successfully forecast things, and how we can measure that ability. And I hope that we've learned something out of this, last couple of years where we were really tested to kind of do this real time and to find models that were effective. And hopefully we've learned a thing or two. And it sounds like you and your team are at the tip of that spear. So thank you so much for sharing this with us. I want to thank everybody who joined us here on Zoom and out on YouTube, and wish everyone a wonderful weekend. And we'll see you later. Bye, everybody.
Thank you. Cheers. Bye-bye.
Thank you, Chris.